Okay, the last thing that we're going to talk about out of this section is something called expected value. Expected value is the most important thing when you're talking about any sort of gaming or gambling system, because I'll show you why here in just a sec. Because it's going to dictate how much money you're going to win or lose if you're the house, or if you're a gambler, it's going to dictate how much money you can expect to win or lose per play of a certain game over the course of many plays. All right, so let me try to explain this to you. Let's make up the simplest craps game ever. I'm going to hand you, excuse me, I'm going to hand you some dice. And I'm going to say, roll the dice. And if you get a 7, I'm going to, let's assume that you bet, I don't know, what's a reasonable bet? $1, okay? If you win, I'm going to hand you your dollar back, and I'm going to take, I'm going to try that again. I'm going to hand you your dollar back, and I'm going to give you, let's go $4. Okay? And if you roll anything other than a 7, I get to take your dollar. All right? So watch this. I'm going to create a probability distribution to model this. Now, think about it this way. I don't have to build that probability distribution that I did before. I don't have to build this guy because my outcomes are going to be based on money. All right? I don't worry. Remember, you either roll a 7 and get paid, or you roll a not 7 and don't get paid. All right, again, I'm overly simplifying a craps game, but we won't, no panicking. All right, watch, check it out. So what did I say? I give you, if you roll a 7, and we know that the probability of rolling a 7 is 1 out of 6. If you roll a 7, I give you your dollar back plus what I say, $4. So you are up $4. You're not up 5 because you had that dollar in your pocket to begin with. Otherwise, you lose $1. All right, so this has to be 5, 6. Now, the expected value of the game, this is sometimes written as E of X, is actually the average value of the game, which is the sum of X times P of X. So in this case, all I have to do is multiply this times this, and this times this, and I add it. Now watch what happens. 4 times a sixth plus -1 times 5/6, and I end up with -1/6, right? Which is approximately equal to what? -17 cents, more or less. It's about what a sixth is, 17 cents. All right? Now, this is where students start getting glassy-eyed and go, what? Again, this doesn't make sense. I didn't make that bet. I can either win 4 or I can lose 1, and you're talking about 17 cents. Okay. Here's the way this works. If you play this game over and over and over again, sometimes you're going to win $4. Sometimes you're going to win, or you're going to lose $1. However, if you take the average of all of those outcomes, right? If you take the average of all of those values, you can expect to lose 17 cents on average every time you play. Now, again, I realize that doesn't qualify as one of the outcomes, but remember, we're talking about an average here. Okay? So think about it. If you're the casino, this is a great game for me. Even though sometimes I'm going to lose big bucks, well, $4, sometimes I'm going to lose big bucks, well, that doesn't frighten me at all, because on average, as long as I can keep you playing, and that's key, as long as I let the law of large numbers come into effect, let's write that out, law of large numbers. As long as I let the law of large numbers do its thing, I am golden, because I can expect to make 17 cents on you on average every time you play. All right, I know I said on average about 19 times, but that's really, really important. But the key is keeping them playing. So think about Megabucks with their $250 million jackpot. Look, somebody's going to win this, but the expected value of the Megabucks slot machine for all of those $250 million jackpots that they pay, there's a ton more people just pulling the handle, losing $5 at a time, $5 at a time, $5 at a time. Because the casino, the house, never gives you a game where the expected value is greater than 0. If they do, they lose money. And there have been some pretty notable cases where people were able to rig the system so that the expected value of a game popped up above 0. We'll talk a little bit more about those in class. Okay? So just a couple quick things. If the expected value of a game is greater than 0, this means that you gain money. Do the math. If the expected value of a game is less than 0, this means you lose money. Lose money. Whoops. Remember, we talked about this earlier in the class. If the expected value of a game equals 0, then you come out even. Nobody wins and nobody loses over the course of many, many plays. Okay? So you could actually tweak these payouts to make the expected value of this game equal 0, which is, it's actually relatively simple to do. Watch this. Let's say that I want x and I have p of x, okay? And I'm going to have 1/6. Again, this is just a really simple problem. I want to make this an even game. So here's what I'm going to do. I'm going to let's say that I bet $1 and I lose $1. And I don't know how much money to give, so I'm going to call this a variable. All right? I don't know what I want my payout to be. So I just simply call that some variable. Well, I know that the expected value of the game is equal to the sum of x times p of x. So I get m6 minus 5/6. If I want the game to be a fair game, then this is going to equal 0, right? So in a puff of algebra, guess what? M is going to be $5 if I solve for m. Think of it the other way. Maybe this is a little bit more, I don't know, nefarious, for lack of a better adjective. What if I want to make a little bit more money? What if I want to actually say, you know what, 17 cents a play just isn't making me enough money. So I need to figure out what to pay out. So instead of making 17 cents a play, I want to make 20 cents a play. We do exactly the same thing. I'm going to go x and p of x. This is how insurance companies do it. We've heard of actuaries. They figure it out, so on average, they make a certain amount of money off of each customer. Think of insurance as just being a great big gambling game. So I'm going to lose $1 5/6 of the time, and I'm going to gain m amount 1/6 of the time. So it's the same problem. I know that e of x is going to be m6 minus 5/6. Only this time now I'm thinking of this from the standpoint of the player because I'm losing $1 when I play. So the casino wants me to lose negative what? 0.2 or negative 1/5, right? All right. So in a puff of algebra, let's see how good I am. M6 equals, what is that? 25 minus 6, what is that? 19 30ths? That's not 19 30ths. What am I doing? So 25 minus 6 is 19. It is 19 30ths. Oh, times 6. So m equals 19 fifths. So now I'm paying out just slightly under $4, right? You see what that is? What would that be? That would be 380. So if I make m equal to 380, so 3/8, what are you doing? 380. So I give you your buck back plus 380. On average, I can count on making 20 cents per customer per play, as long as I keep them playing. Hey, I hope this was instructional. I love this stuff because clearly I'm a Nevada native. I'm a Reno native. Strangely enough, I was born about 2 blocks from where I'm teaching you right now. So it's in my blood, as it were. Thanks for paying attention. And we'll talk a little bit more about Chapter 5 in the next little lesson. All right, have a good day.